Well, hello calculus class. We're going to take a look at section 2.5, limits involving infinity, and I'm going to go back to one of the examples we looked at the first day of class when we were looking at limits, and that is the graph of 1 over x squared. So I just want to pull this up here for you guys to take a look at, just as a reminder. And want to talk a little bit about what we had already said about this. Back in section 2.3 when we were talking just about limits, we had said the limit as x approaches 0 for this particular function 1 over x squared was a d/e. It does not exist. And I said that in that particular section that was going to be the answer you'd most likely see in the back of the book, but we did have this understanding that as we're looking at values closer and closer to 0 from both the left and the right, that we in fact see that it's tending to go towards positive infinity from both sides. So it would be then appropriate to say that the limit as x goes to 0 of 1 over x squared is actually positive infinity. And we would all understand what that means. And this is the first part of limits involving infinity that we're going to talk about. So, you know, we just need to know that this particular quantity, infinity, indicates that the limit doesn't exist. However, in terms of giving more information about the graph, saying that we know it goes to infinity, that the limit from the left and the limit from the right both head to infinity. So the limit as x approaches 0 from the left is equal to the limit as x approaches 0 from the right, which is positive infinity. Again, that's why we're going to go with that, and it's okay to go with that. So we're going to be talking a little bit about that, and then the second thing will be limits involving infinity, where the value of x actually goes to positive and negative infinity. That'll be the second part of this particular video. All right, to be very specific, using some definitions and some limit notation. All right, so let me just get a new page up here. What I want to say is that when we're talking about limits, the limit as x approaches a of f of x equals positive or negative infinity. You know, what are we actually saying that means? That means values of f of x can be made arbitrarily large or small if we have x values approaching the value of a. If x gets close to a. But as we know, x cannot equal a, so we're not necessarily looking at a direct substitution. Many of the times those will be undefined values. So that's what we want to be using as our definition for going off to positive or negative infinity as x approaches a number a. Just as a reminder, with the function f of x equals 1 over x, the limit as x approaches 0 of f of x still does not exist. However, if we want to talk about the left-hand limit, so the limit as x approaches 0 from the left of f of x, we know that that does in fact go to negative infinity, and the limit as x approaches 0 from the right of f of x goes to positive infinity. So, ooh, that looks like 0, 0. Infinity. There you go. We'll have our left and our right hand limits still being able to be defined, but overall the limit as x approaches 0 is not defined for this particular function. All right, let's take a second to talk about something that I know you've already seen. Obviously through pre-calc you've had a discussion of vertical asymptotes. When you saw a tangent, when you saw secant, cosecant, cotangent, you saw functions that had vertical asymptotes. In calculus we just need to make sure that we're formally defining these using limits, and that's what we're going to do right now. That's really kind of the important piece of limits involving infinity, is talking about asymptotes and their definition. So if I want to define the line x equals a, and we know that x equals a constant is just a vertical line, so the line x equals a is called a vertical asymptote. If for f of x, one of the following things occurs. If the limit as x approaches a from the left of f of x is equal to positive or negative infinity, or if the limit as x approaches a from the right of f of x goes to positive or negative infinity, we have ourselves a vertical asymptote. Obviously, if both of those are true and they go to the same value, the limit as x approaches a could go to positive infinity or negative infinity. But even if they go to opposite infinities, so if one goes to positive infinity and one goes to negative infinity, we still have a vertical asymptote at x equals a. Here's another example of a graph for which this is true. So let me just bring this up for you. And I'll stretch it out even, make it a little bigger. Now I'll make this is what I want to make bigger. It doesn't want to get bigger. Alright, so you're just going to have to deal with it. There's the graph of 2x over x minus 2. And as x approaches 2 from the right, the function is going off to positive infinity. As x approaches 2 from the left, the graph is going off to negative infinity. So we would say that x equals 2. Oh. Hope you're not getting dizzy. Sorry about this. X equals 2 is a asymptote for the graph 2x over x minus 2. Here's something that you're a little bit more familiar with. Hopefully you recognize this as the graph of tangent x. So this is f of x equals tan x. And we know that tangent is undefined at odd pi over 2 values. Both positive and negative. So we could write that the limit as x approaches pi over 2, and we'll go pi over 2 from the left on this one, of f of x is equal to positive infinity. Therefore defining x equaling pi over 2 as a vertical asymptote. In calculus, when you're asked to verify that something has a vertical asymptote and you're asked to write its equation, the expectation is that you are giving the vertical asymptote as an x equals equation. You're not just stating pi over 2. So by just writing pi over 2, that's not the equation of the asymptote. So please be very careful about that. If it does ask for an equation, not the value of x, write it in equation form. Alright, some of what you guys took a look at today and finish up for your homework tonight in the Awesome Asymptotes packet had to deal with letting the value of x go to infinity. So at times we look at finding values of x that make f of x really, really large or really, really small, so going to positive or negative infinity. We can also look at the value of x going off to positive or negative infinity and see what effect that has on f of x. Now, you're not guaranteed that the function will always diverge, and for those of you who did some sequence and series stuff last year, you probably did divergent and convergent series. A little bit like that, but not as involved. So for this particular one, let's just talk about a particular function f of x. And what if we consider f of x equaling x squared minus 1 over x squared plus 1? And one of the things that you might right off the bat see is that the numerator factors. It factors to x minus 1, x plus 1, but in fact that's not going to help us in terms of looking at the limit. And the question that I have is as x goes off to positive infinity, what happens to f of x? So essentially what I would like to know is as x goes to positive infinity, what is the limit as x goes to infinity of f of x? Well, one way that we can investigate this is just starting to take a look at some of the values of x, plugging them in and seeing if we can pick up on a pattern which may be happening. So if we were to substitute in the value of x equals 1 into this function and find f of 1, we would get that f of 1 is equal to 0 over 2, which we know to be 0. And then we can start just increasing the value of x. So when x is 2, what would f of 2 be? Well, f of 2 would be 3 over 5, 3/5. we could let x equals 3 and find that f of 3 is equal to 8/10. And we're starting to see that we're definitely getting an increase in the values, that 3/5 is smaller than 8/10 or 4/5. That from 0 to 3/5, 3/5 to 4/5, we're actually increasing the value of f of x as x is increasing. The question is, does that continue on that pattern, or does it stop? Is it approaching a particular number and we just don't see it yet? So let me move that out of the way and continue doing this. If we chose just an arbitrarily large number like x equals 100, and I found f of 100, we would see that f of 100 is equal to 999 divided by 1001. And if you were to go back and actually look at all of the values that I had up here, 0 over 2, 3 over 5, 8 over 10, notice that the numerator and denominator simply differ by a value of 2. And that makes sense because over here the x squared minus 1 and the x squared plus 1 are only differing by the minus 1 and the plus 1, so a net change of 2. And we're seeing that in the fractions. And as you get really large, as x takes on very large numbers, f of x looks like it's approaching a particular value, and that value seems to be 1. And we could continue doing this, but I think 999 over 1001 is pretty darn close to 1. So we know that the limit as x approaches infinity of f of x is equal to 1. And what that means for us is now we have a horizontal asymptote. And the equation of that horizontal asymptote is y equals 1. So much like a vertical asymptote has an equation of x equals a number, the horizontal asymptote has an equation of y equals a number. And we're going to talk more about this in class tomorrow. Just kind of wanted to get the introductory material out of the way so that we can get right into the meat of the examples that I want to do with you, and we can finish up this discussion of limits and move on to the discussion of continuity. Alright, so hopefully that's just a good background of what you might have already seen. Maybe that's some new stuff for you. Tomorrow we'll do some more examples of that. Okay, well, thanks for watching. I'll talk to you later.